Good morning, everyone. Welcome to our ATTAINS training today. I just wanted to let everyone know that you can unmute yourself during the call. Also, if you're calling in, you can use *6 to unmute your phone or *3 to raise your hand, and I can unmute you if you have a question. Also, there's a chat box that everyone can use for any chats. And with that, I'm going to turn it over to Maggie Pierce. She is our presenter for today. Maggie, the floor is yours.
Good morning, everyone. Thank you, Karen. I'm Maggie Pierce. I work in EPA Region 8's Denver office. I'll be presenting Module 3 in our assessment series here. We'll be looking at assessing data for some specific water quality parameters. We won't be able to cover every water quality parameter that's out there, and as I'm sure you guys all know, there's a lot of different ways to assess data. So please chime in with any thoughts that you have on different ways to do things, or any questions that you may have. Let's see, Karen, I am not moving. Oh, there we go. So the objectives for this module are to introduce some basic approaches of assessing some water quality parameters, making a distinction between acute and chronic aquatic life criteria, thinking a little bit about sample size for evaluation of water quality data, and then we'll talk about assessment of a few different specific parameters like DO or dissolved oxygen, pH, temperature, turbidity, nutrients, pathogens, and metals. So first, let's talk about what are numeric water quality criteria. I know it sounds silly to say, but they have numbers in them. The distinction we're making here is with narrative water quality criteria. EPA encourages tribes and states to adopt narrative water quality criteria, which describe a condition or an expectation for a water body or the waters of the reservation. The numeric water quality criteria may be in some tables, they may be scattered throughout the standards, or they may not be. They may not be in standards. Sometimes we use the term criteria to describe these guidelines that EPA puts out. We'll also often call them Section 304A guidelines or nationally recommended guidelines. And these guidelines can be what are adopted into tribal water quality standards, at which point they do become law. But if they're not adopted into tribal water quality standards, they can still be really useful thresholds to use to assess monitoring data. So numeric criteria tend to take three general forms. If they're for a parameter that's toxic and causes a problem for the water body use, they'll often be in a less than form, or they'll have some sort of maximum amount associated with them. An example of this is nitrate. If it's for a water quality parameter that's a good thing and you need a certain amount of it in order for the water body to meet its uses, it'll often be in a greater than form or have a minimum associated with it. And then some parameters will be a range. The classic example of this is pH. It has a sweet spot. There's a problem, it becomes a problem at too low or too high of a value. We often talk about numeric water quality criteria being broken into three components: magnitude, duration, and frequency. This example reads, should not exceed 10 milligrams per liter as an annual average more than 10% of the time. So in this example, the 10 milligrams per liter is the magnitude. It's that concentration. It's not always a concentration. It could be some other sort of value like a loading. The duration is a year. This one's a little more subtle. It doesn't straight up say it's a year. It describes it as an annual average. But from that, we can pull that this criterion is intended to apply as an annual or a yearly value. And then this criterion has an acceptable exceedance frequency or recurrence interval associated with it of 10%. For aquatic life criteria, those tend to be explicit within the water quality standards. For human health criteria, sometimes they're not. They might be in your assessment methodology outside of the water quality standards. Sometimes you have to go looking for that. But a good assumption, if there isn't one specified, is that there's not an acceptable exceedance frequency. So how do you figure out which criteria you want to look at if you're going to assess a water body? Well, a good way to start is to think about how that water body is being used. If your tribe has water quality standards, it's probably identified some designated uses, or they may call them beneficial uses. If you don't have water quality standards, that's okay. You can still think about what you know about that water body for which you have data that you want to assess, and how it's used. And if you don't know much, a good place to always start is with aquatic life criteria or recreation criteria. The Clean Water Act establishes the goal that all waters meet those criteria, so they're a good place to start with. But there are other criteria out there too, other designated uses with associated criteria. Those may be drinking water, cultural and traditional, agriculture, industry. So for aquatic life criteria, because they're something that we want all water bodies to meet, and because they oftentimes are quite stringent and drive assessments on waters, we're going to dig into them just a little bit more. Aquatic life criteria are often broken into acute and chronic criteria. Acute criteria protect against a lethal endpoint, so loss of the organisms, and they tend to be framed in a way that's a high concentration over a short amount of time. Chronic criteria protect against effects that are less than lethal, but still problematic for the aquatic community. It might be reduced growth, reduced ability to prey on other organisms, and they tend to be lower concentrations over longer amounts of time. And this sort of framework that was set up with acute and chronic criteria simply came from observations that organisms can tolerate higher concentrations of contaminants over short amounts of time and lower amounts of concentrations over longer amounts of time. And at the bottom of the screen here, we have an example chloride criterion just to give you a general sense of how those two things might relate to each other. The acute chloride criterion is 860 milligrams per liter, and the chronic is 230 milligrams per liter. The magnitudes, that's what those two values are different between these two criteria. But for the chloride criteria and many aquatic life criteria, the durations are also different, 1 hour versus 4 days. That's 1 hour for acute, 4 days for chronic. But the exceedance frequencies are the same, 1 in 3 years. So now we have a figure. This is looking at the chloride criteria and some data from the Lumi Nation. On the y-axis, we have chloride in terms of milligrams per liter and time in terms of days on the x-axis. The yellow line across the figure is the acute criterion, and the red line across the figure is the chronic criterion. So right off the bat, we can quickly see that we have an exceedance of the acute criterion. And then we also have some exceedances of the red criterion. And I'm sorry, I didn't mention the blue dots are the measured data from this particular water body. So looking at the timeline here, the y or the x-axis across the bottom, it looks like these data are just about daily, which is pretty frequent, I think. I think it's rare to see this frequent of data, but that's great. That lets us do some things that we might not otherwise be able to do to assess these data. So as you may recall me mentioning, or as you may see at the top of the figure there, the acute criterion is a 1 hour average criterion. So with daily data, there's nothing else we really need to do. We're already at, at a value that's greater than a 1 hour. We're at a daily value. The chronic value, on the other hand, is a 4-day average. And we do have these pretty frequent data. So we can actually calculate some 4-day averages. And this figure has really honed in on this kind of day 11 to day 17 time period, because that's where it appears like there's the most potential for an exceedance of the chronic criterion to occur. So fortunately, someone has gone and calculated the 4-day averages here in the green text, so we don't have to do it. And indeed, there are exceedances of the chronic criterion as a 4-day average, in addition to exceedances of the acute criterion. So in this example, this water body would definitely be impaired for chloride. And I just want to point out that in this particular example, there are really frequent data, and that's great. That's probably not going to be a situation that most of us are in. So a lot of times you're probably going to be using the same data point without doing anything to it, without doing any averages or anything, to compare against both the acute and chronic criterion, and that's okay. And that brings us to a brief touch on sample size. As you guys can probably guess, more is generally better. But I do think it's worth sort of stepping back and thinking about how much data do I really need in a world of limited time and resources. It's always good to ask yourself that question. And I think it's helpful to think about what your question is. What parameters are you going to be assessing? Before you go out and start collecting data for those, it would be good to take a look at the criteria or the thresholds that you're going to use for assessment, whether they're in your tribal water quality standards or whether they're the EPA 304A recommendations. It's possible the criteria have some sort of seasonal component to them. It might also be good to know whether the criteria have a particular duration, whether they're instantaneous, or whether they are over a long amount of time and are intended to represent a long amount of time. Similar to that, are they, is there a metric associated with them? As I mentioned before, are they instantaneous? Are they an average? Are they some sort of percentile? I think it's also useful to think about the water body that you're trying to assess. How variable is it? The more variable it is, the more data you may want to try and get. And when I'm talking about variability, I'm thinking about variability in terms of flow, air or water temperature, and then also space. If you have a fast flowing small stream, you may not be too worried about finding, multiple samples to represent that water body. But if you have a lake or reservoir that stratifies, you might want to get more than one sample to represent that water body. And then I also think it's useful to think about, well, what are the implications of this assessment that I want to conduct? Are the stakes high or are the stakes relatively low? Are you conducting an assessment to just sort of generally get a sense of the conditions on your reservation? Are you conducting an assessment because you need to revise a permit or there's a possible resource expenditure that might be made? If the implications and the stakes are a little bit higher, you might want to collect a little more data to be a little more confident and be able to tell more of a story. And then at the bottom here, we have a note about minimum sample sizes. Sometimes you'll see them written out in a water quality standard, but they're technically not a water quality standard. Sometimes you'll see them written in your assessment methodologies, and minimum sample sizes are useful, and they're definitely good to think about. But there are situations where you might be able to make a decision without having met a minimum sample size in the face of overwhelming evidence. And an example of this I'm thinking is maybe you have a minimum sample size of 5 in your assessment methodology, and for whatever reason, maybe because of COVID or, for whatever reason, you weren't able to get out and get all 5 samples. You only got 3, but it turns out 2 of those samples are exceeding an acute criterion, which has no acceptable exceedance frequency associated with it. That could be an example of a situation where you're looking at overwhelming evidence that there's a problem in this water body. And then the intent of this slide is just to sort of illustrate this sample size idea a little bit more. On the y-axis, we've got a generic pollutant concentration, and on the x-axis, we've got time in terms of days. And then the red line represents a criterion. And if you imagine just the purple dots having been collected, those purple samples, the 3 ones there, you might think that everything's okay and the criterion is being met. But if you go and collect more frequent data, you get a different story. You see some exceedances of the criterion, and then you also start to wonder, this is a long amount of time here. It looks like maybe a weekly sample over 90 days. Maybe there's something seasonal going on here. Maybe it was just some sort of discharge or something, who knows, but it looks like there's some sort of pattern going on in this water body. And then this slide is just illustrating different types of parameters for which water quality exists. There's DO, or dissolved oxygen, pH, temperature, and turbidity. We call those conventional parameters. Nutrients like phosphorus and nitrogen. You can even have criteria for biology like macroinvertebrates or fish or algae. There are criteria for fecal indicator bacteria like E. coli and enterococci. And then there are toxics criteria for things like metals and ammonia. So first we'll talk some about assessment of conventional pollutants. The Clean Water Act actually defines conventional pollutants. That's where this kind of odd term came from. I just think of them as things that you measure with a sonde or a probe. And I think the most sort of notable thing about conventional pollutants, at least from a data collection standpoint, is that they can be either GRAB or continuous data. And having either GRAB or continuous data, you might want to have an assessment methodology to address both situations. And if you're not familiar with this concept, we'll talk about it a little bit more, hopefully illustrate a little bit on this slide. Dissolved oxygen is a constituent that is critical for life. It's one of those parameters where it can get too low, so it's oftentimes established as a greater than or a minimum criteria. It has a relationship with temperature. In the upper right-hand corner, we have a figure illustrating some GRAB data. It looks like it's about daily for dissolved oxygen. And then in the lower right-hand corner, we have a figure illustrating what more continuous data might look like. And so, I think the real sort of item of note is that when you see the lower right-hand figure, you can see that the dissolved oxygen is varying over a single day. And it goes up and it comes down and it bottoms out usually in the wee hours of the morning. So here, this is a lot of text on this slide, I know, but I wanted to share an example of a dissolved oxygen criterion. This is from the Fond du Lac Band of Lake Superior, Chippewa, and my apologies in advance if I mispronounce any names here. I haven't worked with everyone, so I might not have experience saying them all. But I think there are a couple things to note from this slide. And one of them is that the Fond du Lac have established two different types of dissolved oxygen criteria. They have a daily minimum of 5 milligrams per liter for all their waters on their reservation. And then they have another minimum, a daily minimum of 8 milligrams per liter to protect early life stages of cold water fish. And this is something to think about. If you have, if your reservation covers a wide range of elevation or just different water body types, if you just know, well, this water tends to run much colder naturally, it has a cold water fishery, there may be reasons to apply different criteria to cover different types of waters. The tribal water quality standards probably go on to link this higher 8 milligram per liter dissolved oxygen criterion to a specific use and then link that to some specific waters. But if it doesn't, you might have to do a little extra work, but you could still do it. You could go based upon what you know about that water, what you've observed in that water. You could talk to your fishery and game department if you happen to have one. You could talk to some other resource management folks in the area to help you figure out, well, I'm looking at, water body X, which criterion is the best to assess. Here is another example of some dissolved oxygen criteria from the Maka tribe. What's different about this one from the previous example we saw is that they have two different types of averaging periods. So we have two different uses here as well, kind of similar to how the Fond du Lac Band of Lake Superior Chippewa set it up. But within those two different uses, they have a 7-day average and a minimum criteria. And they have identified two different subcategories of their aquatic life use. They've got the salmon and trout spawning and salmon and trout rearing and migration. And that the criteria that apply to the spawning use are a little higher, a little more stringent than those that apply to the other use. And so I think one thing that's good to know if you're getting ready to collect some data and conduct an assessment of DO criteria is what sort of averaging period are you looking at? And do you have more than one that you need to think about? And, you know, if you can, it's great to get data to be able to assess all criteria, or maybe you think of them as sub-criteria or subcomponents that apply. So this figure has a lot going on. Let's break it down. So on the y-axis here, we've got dissolved oxygen in terms of concentration. On the x-axis, we have time in terms of days. The solid red line is the minimum 9.5 milligram per liter criterion that we saw from the previous slide with the Maka tribe. This dashed red line is the 7-day average criterion. And then the blue dots are individual measured data points. And the dashed blue line is an average, a 7-day average of those individual measured data points. So we can see that the 7-day average, that blue dotted line, is higher than the 7-day average criterion, that red dashed line. So that's good. That one meets. But then we can also see that on August 11th, the 7 milligrams per liter value here dipped below this 9.5 instantaneous minimum. So that's a problem. Without any sort of acceptable exceedance frequency, even though the 7-day average is meeting, this instantaneous minimum is not. So this water body would likely be impaired for dissolved oxygen unless they had some sort of acceptable exceedance frequency associated with it. So for me, the takeaway from this slide is that when you have sufficient data to do so, you want to compare apples to apples. And you want to compare a 7-day average to a 7-day average criterion if possible, and you want to compare instantaneous minima to single data points, not some sort of averaged criterion or averaged value. So this figure here is an example of pH criteria. As I mentioned earlier, it's a range. There's a minimum and a maximum. There's criteria for both aquatic life and human health, but the aquatic life criteria generally are a little more stringent. They're a little more of a narrow band there. So on the y-axis, we've got pH, and on the x-axis, we've got time in terms of days. And there's a number of pH samples that were taken, and the approach that this figure takes is to put the pH criteria up as the minimum and the maximum, and then plot the data and see what falls outside of those two lines. It's a pretty kind of neat and simple way to see where the criteria land. And we've got 2 points that are less than the minimum, so that's a problem. Without some sort of acceptable exceedance frequency, this water body would be impaired for pH. So then in this slide, I know I'm breaking some rules of PowerPoint presentation by putting up yet another busy slide, but I just wanted to make the point that, in this presentation, we've been looking at a lot of figures and graphs, and I think that that can be a helpful way to get familiar with a complicated water quality standard or criteria threshold. If you're a visual person, it can be a useful exercise to go and do that. But sometimes, to tell a story and make a decision about whether an impairment exists or not, you don't have to go that route. You might just want to generate a spreadsheet and a table if you're comfortable with those types of presentation materials. And in this example, this is a pH example. We've got 3 monitoring sites, and we've got some summary statistics about the data that were collected at those sites. And this was pH, and then so in this yellow column here, we've just calculated the number of exceedances, and in this instance, there is no acceptable exceedance frequency, so anything outside of the acceptable pH range is a problem. And we can see that 2 of the sites have some exceedances of the pH criteria. So next we'll be talking about temperature criteria. Temperature criteria are typically associated with aquatic life use support. Oftentimes they're broken out between warm water and cold water type uses, or even other more specific aquatic life uses. There's two general forms that temperature criteria tend to take. You'll see some that are a relative change, some sort of acceptable increment above background or a natural condition. And it'll be maybe even described as a delta. You'll hear some people use that term as well. And then the other form that you'll often see is based upon the thermal requirements of the aquatic community. So, you know, there's been a fair amount of research done on especially fish and looking at what their thermal requirements are. And so that's kind of the other main category of temperature criteria you'll see. And it will just be some sort of temperature value. It won't be some sort of relative change usually. So in this example, we have an illustration of the relative change concept from the Pueblo of Laguna's temperature criteria. This blue squiggly line with the arrow on it represents a water body. The black arrow coming in is a point source discharge. And their criteria are based upon an acceptable amount of change from an upstream to a downstream relative to a point source. That's upstream to downstream around a point source. So it's important to have data from both of those locations. And here's another figure with a lot going on. But first, let's read the Pueblo of Laguna's criteria over on the left here. It says no increase in the weekly average of the maximum daily temperature between upstream downstream locations that is greater than 2.7 degrees Celsius. So on the figure, on the y-axis, we've got maximum daily water temperatures. On the x-axis, we have time. The blue line represents the data that were collected at the upstream monitoring location, and the red line follows the data that were collected at the downstream monitoring location. Now, these are individual data points, each of these little dots along the line, and their temperature criterion is based upon a weekly average. So these X's with the lines through them were calculated to represent that weekly average value. So we have about 3 of those. I guess it was about a 3-week period that they had data over. And we see here that at where they had each of those 7-day averages, they calculated one for the upstream and one for the downstream. And then they subtracted the downstream from the upstream. And at this first week here, that value was 2.9. These numbers on the figure is the difference in the weekly average temperatures. And 2.9 is greater than that acceptable amount of change of 2.7 degrees Celsius. So they've got a temperature problem here for that location. Then I just wanted to share an example of what a biologically based temperature criterion might look like. This is from the Swinomish tribe. Similar to the Pueblo of Laguna example we saw, they also have a 7-day average of daily maximum temperatures. And theirs is specific to a salmon and trout use. And it's just a flat 16 degrees Celsius value that's their acceptable highest 7-day average maximum temperature. So there's no sort of change component to it. So next we'll be talking about turbidity. Turbidity is a measure of the cloudiness of water. As you can imagine, there's a wide range of natural conditions associated with turbidity. Turbidity is a parameter that is affected by many different types of water chemicals, total suspended solids or TSS, color, algae, all these things can contribute to turbidity. EPA established some ecoregional criteria back in the early 2000s. For streams and rivers, the criteria were straight up in the form of turbidity. For lakes and reservoirs, it's sort of a related indirect measure of turbidity in terms of Secchi depth. And then EPA also had some very old 304A criteria recommendations for turbidity. Now we're going to look at a couple of examples of turbidity criteria, similar to the temperature example that we were talking about. There's kind of 2 different basic forms that are most common to see. That doesn't mean there couldn't be other forms that work better. But the two kind of common forms you'll see is one that's, again, this relative change idea, and that's relative change to background or a natural condition. And then sometimes you'll see something that just specifies a absolute value, a magnitude to not be exceeded. So now we're going to look a little bit more closely at turbidity criteria from the Pueblo of Sandia. On the left, we've written their turbidity criteria. It's quite complicated. It reads, turbidity shall not exceed 5 NTU over background when background turbidity is 50 NTU or less, with no more than a 10% increase when background turbidity is more than 50 NTU. Background turbidity shall be measured at a point immediately upstream of the turbidity causing activity. So this criterion is kind of what I think of as like a two-pronged criterion. It's describing two different criteria and kind of two different subcomponents. Are you guys noticing a theme? This is happening a lot. So for me, the first thing I would want to do is figure out which of these applies. Is it the 5 NTU over background, or is it the 10% over background? And so that all hinges on whether background is 50 NTU or less. So this figure on this slide, the purple diamonds represent the upstream or background data. And we can look at where those fall. And sorry, we have turbidity on the y-axis and time in terms of days on the x-axis. And all our purple diamonds are falling below 50 NTU turbidity. So what that's letting me know is, okay, it's just this first prong that applies, this 5 NTU over background. So what these guys have done, which is something really interesting, I don't know that I would have ever thought about doing it this way, but it's actually kind of cool. They took their background purple diamonds and added 5 onto it and generated this green line. Then they plotted their upstream data, these orange X's with the line through it. And all they had to do was look and see if any of the orange X's were above their green line. And indeed, we've got a couple points, not exactly, kind of in that October to April timeframe that are exceeding the criteria. So we've got a turbidity problem in this water. So next we're going to be talking about nutrient parameters. Most often that's nitrogen and phosphorus. Nutrients are essential for aquatic life. They're food for algae and plants, like fertilizer in your garden. However, too much of them can lead to excessive algal growth. That's a condition we often call eutrophication. Sometimes harmful algae will start developing under those conditions. Harmful algae may produce toxins. And then the dead and decaying algae are eaten up by the bacteria, and that can cause a dip in dissolved oxygen, which can lead to fish kills. Most often, nutrient criteria are associated with protection of the aquatic life use. So there's kind of this paradigm out there that freshwater systems are more sensitive to phosphorus or limited by phosphorus, and saltwater systems are more sensitive to nitrogen or limited by nitrogen. What we see oftentimes is that you need to really understand your water body and what might be limiting. It might be that you have co-limitation between both of them. It might be that it changes over time. It's just important to understand nutrients within the context of a specific water body or a specific region. So here's another slide with a whole lot of text. And these are 4 different examples of nutrient criteria. And I'll not read all these criteria, but I'll summarize some of my takeaways from these different 4 examples. And it's that sometimes the type of nutrient varies. If you'll look, you'll see some of these only limit phosphorus, some of them limit both phosphorus and nitrogen. We don't see it here because I think they're all for freshwaters, but you could theoretically have something that only limits nitrogen. Another takeaway is that the chemical fraction can vary. And when I say chemical fraction, I mean the component of the nutrient. So in the 3rd example from the top, They've specified total inorganic nitrogen specifically as their criterion, and that's probably driven either by specifically what they saw on their reservation or the type of data that they had available to them. And then one other thing I wanted to flag, interestingly, you don't see it in any of these examples, but nutrient criteria often have a seasonal component to them, especially in colder places, maybe not so much in warm places where things don't change too much year round, but sometimes nutrient criteria only apply a certain season. Oh, and there is one more thing I wanted to flag in the bottom example, the one at the bottom there. This tribe, the Oneida Nation, has established different criteria for different types of water bodies. And it's interesting what they've done here. So they've done phosphorus shall not exceed 25 micrograms per liter for any lake or reservoir. Then they have 50 micrograms per liter phosphorus for any stream. And then, and I'm sorry, that's any stream that flows directly into a reservoir or lake. And then they have another criterion for streams that do not flow into reservoirs or lakes. So water body type matters for nutrients. And as I mentioned, you most often see nutrient criteria for the aquatic life use, but it's possible to have nutrient criteria for other uses as well. We've got an example of total inorganic nitrogen from the Isleta tribe, and then an example, and I'm sorry, that was for the primary contact ceremonial use. And then we've got an example from the Laguna tribe for nitrates to protect the drinking water use. So third here, we'll be talking about assessment of fecal indicator bacteria. Nowadays, it's mostly E. coli or enterococci, but you may also see fecal coliforms out there. These criteria, unlike a lot of the other criteria we've been talking about, are really designed to protect human health. They're often applied to recreational or ceremonial and traditional type uses, any sorts of uses where humans may be immersing and have the potential to ingest water. And then the criteria themselves are really indicators of fecal contamination. So they're acting as surrogates for a whole slew of different pathogens that could be present in that water body that may cause illness. Then this table at the bottom here are EPA's current 2012 recreational criteria. As you'll see, there's two recommendations. We're just going to focus on the first recommendation. There's a recommendation for enterococci for both marine and freshwaters, and E. coli for just freshwaters. And then for both of those parameters, the item of note here is that there's two columns. There's this column that says GM, which is geometric mean, and then STV, statistical threshold value. And it's not framed in an acute and chronic sort of, it's not using those words, but it's kind of a similar idea. This geometric mean applies over a 30 or 60-day period, and it's to represent this longer term sort of water quality condition to protect human health. The statistical threshold value is intended to be implemented as a 90th percentile and represents this higher concentration, this higher level of what is acceptable to protect human health from fecal contamination. So they work together. On this slide, we have an example from the Navajo tribe. Their E. coli criterion is 126 colony forming units per 100 milliliters as a geometric mean, with a minimum of 4 samples in 30 days. And then it also looks like they have a recreation season specified, and it's probably April through October based on the data we have here. So because of the duration, the averaging period associated with their criterion, they've gone and broken it out by month, which totally makes sense. And they've calculated their geometric means. And we see we've got a number of exceedances, June, July, August, and September. However, in this example, the Navajo have also specified that they want 4 samples in a 30-day period. And while that's technically not something that EPA would consider part of the water quality standard, it's still an important part of their assessment. And so over in this right-hand column here, you guys may notice that a couple of these months don't meet the minimum sample size. So here in this instance, we've weeded out the months that don't meet the minimum sample size and just focused on where the exceedances occur, where the data are sufficient. And, you know, earlier I was talking about that situation where you may have overwhelming evidence, even if you don't meet a sample size. I don't think this is one of those. I mean, E. coli is a parameter that we see a lot of variability with. And it's really, the geometric mean is really intended to represent kind of an average condition. So I think having a minimum sample size is pretty appropriate. And it makes sense to me that they would not focus on those exceedances where they don't have adequate data, and they would focus on the months where they do have adequate data. However, they might note to themselves, hey, you know, next year, let's try and go get a little more data in August and September and see what's going on there. So on this slide, we're going to look at the other component of the Navajo recreational criteria. So EPA's current recommendation is for a statistical threshold value, but previously we had recommended, and a lot of folks adopted, a single sample maximum, and the Navajo still have that. And I like the single sample maximum. It's very easy and straightforward to assess, makes a lot of sense. Unlike the geomean, there's no duration or frequency associated with the single sample maximum because it's a threshold that's intended to be met at all times. So in this example, we have E. coli on the y-axis, we've got time on the x-axis. The red line represents their single sample maximum of 235, and the blue dots are their measured data. And given that this is a criterion that's supposed to be met at all times, we can pretty quickly see, oh man, we've got some exceedances of the single sample maximum. And somebody's done the math for us here, and that's 11 out of 31 samples, or 35% that are exceeding. So assuming these data are from the same water body that those previous data were from, they've got exceedances of both the geomean and their single sample maximum, the two prongs of their recreational criteria. So next we're going to be talking about metals. Metals criteria exist to protect both human health and aquatic life. Some of them are hardness based. The metals criteria for aquatic life tend to be a little bit more stringent than the human health, generally speaking. That's not the case in all examples or in all cases. We have an example from the Grand Portage tribe here in this table, and these are specifically hardness-based criteria. So the hardness-based criteria have an input. They're just an equation, and you need to have coincident hardness data. So hardness data taken at the same time as you took your metal sample in order to be able to assess the criteria and see where you land. That's the input. It's also important when you're assessing metals criteria to look at what fraction your tribal water quality standards may specify, if they specify one. If they don't specify a fraction, or if you don't have tribal water quality standards, EPA recommends using the dissolved, but you could still do it with the total. You just want to make sure you get the math right and you're comparing apples to apples. And then similar, you know, as we talked about before, the aquatic life criteria are split into acute and chronic, and that's the case for most metals standards and the hardness-based metals standards themselves. Most metals have an exceedance frequency of 1 in 3 years. And so on this figure here, we've got dissolved iron, and we see that the red line is the chronic iron criterion, and there's one dot above it, one measured data point that's exceeding the chronic criterion for iron. So at least from this data set, they're sitting at 1 exceedance. So they might still be okay. If there's no more data from this water body, they might be just at that 1 and 3 years exceedance, or no more data that includes an exceedance. If this is the entire data set, then they're probably okay. If there's more data that is considered representative and appropriate to include in this assessment, and it also includes an exceedance, then that would put them over the acceptable exceedance frequency. They'd have 2 exceedances, but as it's sitting, just looking at this data, they're within the acceptable exceedance frequency. So when I got this presentation, it suggested using a calculator to calculate hardness-based criteria. Don't do that. Email and reach out to your regional standards contact or me if you're interested in looking at hardness-based metals criteria, and we'll send you a spreadsheet. That's a lot easier. This is an example of what the spreadsheet would look like. It looks complicated, but it's plug and chug. If you're comfortable with Excel, you can definitely do it. And with that, I will stop talking, and thank you guys so much for the chance to present and see if there are any questions, any comments or thoughts.
So far, I don't see any questions in the chat box. Does anybody have any questions for Maggie? If you're calling in, you can hit *3 to raise your hand and I can unmute you. Also, if you have a question after the recording today, I can always send Maggie an email and forward your question to her. If you think of something afterwards, you can send it to me. I don't think we have any questions. Thank you, Maggie, for presenting today. We really do appreciate it. If
Sure,
there's
thank
not
you so much.
any questions, I think we'll end this session for today. Thank you, everyone, for joining us. We really appreciate it. And again, if you have any questions after the fact, just send them to me. I'll be glad to forward them. Everyone, have a good afternoon. Thank you.